Okay, so maybe we can get started. All right, so today we're looking at chapter 3 of the Hugging Face course. And this chapter is kind of like bringing together all of the components that we've been looking at in the first two chapters. So just as a recap, in the first chapter, we looked at sort of the concepts around the transformer and some concepts around tokenization and pre-training. And in chapter 2, we started taking a deep dive into what really happens inside this pipeline API that we were using a lot in the first chapter, and trying to really unpack sort of how to train a model, or at least how to understand the inputs and outputs of a model, and also the inputs and outputs for the tokenizer. So today we're actually going to bring this all together, and we're going to do a couple of things. We're going to look at the Datasets Library, which is this very nifty library developed by Hugging Face for processing datasets of more or less any size. And then we're going to train our very first model using something called the trainer. And the trainer is an API which basically wraps a lot of the complexity around writing your own training loop in PyTorch or TensorFlow. And then we're going to sort of take we're going to kind of unpack what's going on in some sense in that trainer by writing our own training loop in PyTorch. And this will be a great excuse to introduce a very cool library that Sylvain has developed called Hugging Face Accelerate. And this library is really designed for doing what's called distributed training. So how you can kind of speed up your training when you've got multiple GPUs or potentially even TPUs, which is what we'll see today in Google Colab. And of course, if there's any questions, just ask them in the chat at any time, and I'll be pausing at various points to take time to answer them. And so maybe just to start, the kind of ecosystem that we kind of have at Hugging Face at the moment roughly revolves around these sort of components. So we've got the hub, which we've seen several times now already. And we use the hub for both loading models in transformers, loading tokenizers, and also loading datasets. And then transformers interacts with the datasets library, as we'll see today, as a way of training our models. And then once the models are trained, we can then push them back to the hub so that then we can share them with our colleagues, and we can also interact with them using some of the widgets that are developed by the Hugging Face team. So with that, let's take a quick look at the Datasets Library. So the Datasets Library is a kind of general purpose library for processing datasets of more or less any type. So originally it was specifically for text datasets for NLP, but since then it's kind of grown into something that can handle images, audio, and over time we'll have things like time series and so on. And the main power of this library is that it provides a kind of uniform API for processing data. And at least for me personally, this has been one of the biggest productivity gains in my sort of career as a data scientist, because previously, like, I was always having to manipulate different types of data, CSV, JSON, text, whatever. And each time it was always a little bit idiosyncratic, and you had to write your own sort of custom like functions for dealing with all these data types. And the Datasets Library provides a very simple API where you can basically load a data set more or less in one line of code, and then you can process it using something called the map function, which we'll discuss in more detail today. And more or less with this map function, you can kind of do extremely like fast and crazy processing, even on monster data sets that are like, a terabyte in size. You can actually process this on your laptop because this does a very clever kind of lazy loading of memory using something called Apache Arrow. Okay, so let me just have a quick look. Great, cool. So maybe what we can do is we can start by looking at this introductory video on the Datasets Library. So I'm going to play this, and please let me know if you can't hear it.
the Hugging Face Datasets Library. A quick overview. The Hugging Face Datasets Library is a library that provides an API to quickly download many public datasets and preprocess them. In this video, we'll explore how to do that. The downloading part is easy with the load dataset function. You can directly download and cache a dataset from its identifier on the dataset hub. Here, we fetch the ArmorPC dataset from the glue benchmark, which is a dataset containing pairs of sentences, where the task is to determine the paraphrases. The object returned by the load dataset function is a dataset dict, which is a sort of dictionary containing each split of our dataset. You can access each split by indexing with its name. This split is then an instance of the dataset class with columns, here sentence 1, sentence 2, labeled on IDX, and rows. We can access a given element by its index. The amazing thing about the Hugging Face Datasets library is that everything is saved to disk using Apache Arrow, which means that even if your dataset is huge, you won't get out of RAM. Only the elements you request are loaded in memory. Accessing a slice of your dataset is as easy as one element. The result is then a dictionary with list of values for each case. Here, the list of labels, the list of first sentences, and the list of second sentences. The features attribute of a dataset gives us more information about its columns. In particular, we can see here it gives us a correspondence between the integers and names for the labels. 0 stands for not equivalent and 1 for equivalent. To preprocess all the elements of our dataset, we need to tokenize them. Have a look at the video preprocess sentence pairs for a refresher. But you just have to send the two sentences to the tokenizer with some additional keyword arguments. Here we indicate a maximum length of 128 and pad inputs shorter than its length, truncate inputs that are longer. We put all of this in a tokenized function that we can directly apply to all the splits in our dataset with the map method. As long as the function returns a dictionary-like object, the map method will add new columns as needed or update existing ones. To speed up preprocessing and take advantage of the fact our tokenizer is backed by Rust, thanks to the Hugging Face Tokenizers library, we can process several elements at the same time in our tokenized function using the batch equal true argument. Since the tokenizer can handle list of first sentences, list of second sentences, the tokenized function does not need to change for this. You can also use multiprocessing with the map method. Check out its documentation, linked below. Once this is done, we're almost ready for training. We just remove the columns we don't need anymore with the remove columns method. We name label to labels, since the models from the Hugging Face Transformers library expect that, and set the output format to a desired backend, Torch, TensorFlow, or NumPy. If needed, we can also generate a short sample of a dataset using the select method.
Great. So that was a whirlwind tour of the Datasets library. Are there any questions at this stage before we dive into some code? Okay, so feel free to post them in the chat as they come. So one thing I just want to mention that might be useful. So on the Hugging Face Hub, we have looked at the models hub in the last lesson. And today we're going to kind of be looking a lot more closely at the data sets. And there was a question last week about sort of how do you figure out like a good choice of model for, say, multi-class versus multi-label. And at the time we sort of realized that there's no sort of easy way of like filtering these types of models. But it turns out that for data sets, there is a little bit better search for this. So for example, if I'm working on a new project, one of the fastest ways to get results early is to basically build a sort of baseline or a prototype using some public data. This is often much cheaper and faster than waiting for to get permission to access data in your company or waiting for some domain experts to help you with the labeling. And so, for example, if we were looking at like maybe like a multi-class thing, maybe I would pick, say, text classification. And then there are other tags here that I can sort of filter by. So just in case I was interested in question answering, I could select that. And then inside text classification, there are a set of subtasks that we can look at. So for example, here I can maybe select multi-label classification. And then this will return a range of data sets which are candidates for the multi-label case. So perhaps I'm doing something about fake news, then I can look at this data set called Fake News English, and vice versa. So the Datasets Hub is a great way of like bootstrapping your machine learning projects at work. And I've found this is a great way also of finding some interesting data sets that maybe go beyond the standard ones that you often see in NLP. So almost everyone uses IMDb movie reviews to show their training, but there's a lot of extra things here that are quite interesting and challenging because many of these are community provided. And just a side note, if you have an interesting data set that you think would be valuable to the community, you can either contribute it directly to the datasets repository. And so inside the datasets repository, we have a datasets folder which has all of these hundreds of datasets that are basically reviewed and curated by the Hugging Face team. So you can open a pull request and there's instructions in the documentation on how to do this. Or if you wish to provide a community data set, which is something that more or less you don't have to integrate into the library directly, you can also do that. And there are some links in the documentation on how to basically submit data sets to the hub. So let's have a look if there's any questions. None so far. Great. So maybe Omar can put some links to that community versus canonical data sets. Okay, so there's a question from SRM Suma. Datasets library looks very specific to NLP. I couldn't find many datasets related to vision. Is there a limitation to host vision related data? So the short answer is no, there isn't a limitation in the library. It's just that we haven't devoted a lot of effort to integrating vision datasets. And if you have some ideas of vision datasets you would like to add, by all means, feel free to either open a PR in the Datasets library or just reach out in the forums. Basically, at the moment, we have, if I look here, let's see, can I find vision? Do we have a tag for vision? Let's have a look. So I don't think we have a tag for vision yet. But I know that we have, let's see, I think we have CFAR. Oh, we don't have CFAR, maybe MNIST. Oh, interesting. I was fairly sure we had these data sets. Okay, so maybe some of these vision data sets are not yet, that's because I have this, okay, CFAR. Yeah, good. Okay, so we have CFAR 10, CFAR 100, and these data sets you can use using the datasets library. And there's also others, I think I'm pretty sure MNIST is here. So there's fashion, MNIST, and so on. So great question. So I think I can chuck the link in the chat here. So this is the link to MNIST. Let's put this here. Cool. So I hope that answers your question, SRM Suma. Okay, so now maybe what we can do to start with is let's have a sort of look at the collab for the Datasets library so we kind of get our hands dirty with this. So as usual, the first thing I want to do is install datasets and transformers, and I'm going to use the capture magic command to capture all the pip junk that comes out. So once this will take a few minutes. And remember that the basic process in the sort of transformers workflow is we first we need a tokenizer to convert our raw text into input IDs, and then we need a model to process those input IDs and convert them into numerical outputs that we can build predictions on. So basically here I'm just instantiating a tokenizer and a model. So this is going to be BERT base uncased, and this model is an auto model for sequence classification. So it's a text classification head that we're adding on top of the pre-trained model. And this is just a little code snippet that shows an example of how to process basically the raw sequences, convert them into input IDs, and then pass this and the labels through the model. Okay, but we saw that last week, so should be clear. The thing that is more interesting for us today is to start looking at the Datasets Library. So the first thing, or the most common thing you're going to encounter is the load dataset function. And if we just have a look at this load dataset function, you can see that it has a lot of different arguments that you can provide. The most common ones that I use are the path, which is essentially the name of the dataset. This is what you will see, for example, on the hub. So in this case, we have glue, but it could be MNIST, it could be whatever. And many datasets on the hub, they often have configurations which are sort of like subsets. So for example, glue is a benchmark which has many different tasks, and each task has a name. So here we have the Microsoft paraphrase comprehension task. And so if you want to access a subtask or a subset in a given dataset, you use this name argument. And then the other one that we'll see that is really common is to specify the split. So a lot of the time, by default, it will return all the splits that are defined in the library. So here we're getting a train, validation, and test split. But sometimes you just want the train split, and so you can specify those explicitly, and I'll show you how. Okay, so now when we do load dataset, we get a datasets object. And there are two sort of types of objects you'll typically see. So the most common one you'll get at the start is something called a dataset dict. And this is, you can think of it as basically a dictionary where the keys are just a string that correspond to the split. And the values are something called a dataset object. So let's just have a look at one of these examples here. So if I index into the train key or the train set, I'm going to get now a dataset object. And if I look at the first element in that dataset object, I've got an ID, I've got a label, and I've got the two sentences that I need to figure out if one is a paraphrase of the other or not. So in this case, we can see that the first sentence says, Ambrosi accused his brother, whom he called the witness, of deliberately distorting his evidence. And the second sentence says, referring to him as only the witness, Ambrosi accused his brother of deliberately distorting the evidence. So that's a pretty good example of the second sentence being or maybe the first one being a paraphrase of the second one. So it's a bit shorter and it captures the same information. And we can see that the label here is 1, which as a guess is probably indicating that that's true. It is a paraphrase. Okay, so just to unpack a little bit this dataset dict versus dataset thing. So, because this was a bit confusing to me the first time I saw this. So we know that the raw datasets are given by this dataset dict object. And this dataset dict object has these keys, right? So we have train, validation, and test set. And if we look at just like a normal sort of Python dictionary, if we look at the values, then we get now a dictionary, or we get a list of the different values. So just think of dataset dict as a dictionary which maps keys or splits to datasets. And the thing that you do nearly all of your work or your heavy work on are actually the dataset objects. So if we look at a dataset object, so this raw train dataset, this dataset object has a large number of operations that we can do, and we're going to see some of them today. So we can add columns, we can do filtering, we can load from different formats, we can extract some information about the data. So maybe let's have a look at that. If we look at the info attribute of a data set, this will often tell us, maybe we can print it. This will, okay, that's like that. So this will tell us a bit of a description about the data set itself, and there's a bunch of information about the data types and so on. So yeah, basically just remember that data set is the thing that we're going to be doing most of our work on, and dataset dict is just a way of collecting all the splits together. So let's just see if there's any questions. None so far. Okay, good. So One of the important aspects of a data set is that it has essentially types. So one of the things that you may have experienced in your work is that most of the data you deal with is very like messy, or maybe it has like it's like a CSV file and you've got a mix of strings and numbers and so on and so forth. And what the Datasets Library does is it defines very explicitly what the types should be for every column in the dataset. And so this is very useful because it allows you to catch errors earlier and also to do some very fast processing. So if you look at the features attribute of a dataset, what you'll get is a dictionary which shows you essentially the column name as a key and then the data type for that column. And so we can see here that indeed sentence 1 is a string. So we get something called a value type, and here it specifies a string. But the other one that's kind of interesting is maybe the label. So here, the label column, it's not just an integer. I mean, it could be an integer, but Datasets provides something called a class label type. And this class label type contains information about the number of classes that we have, or the number of unique labels that we have, what the names of those labels are. And those are basically the two things that you need to know, is just the names and the number of classes. And then we can see that, for example, the ID is just got a data type of integer 32. And so one of the things you can do with these features, so one thing that's like kind of nice, so features is just a dictionary, so we can access the values by key. So if we get the label, this is going to give us this class label type. And this class label type has a couple of handy functions. So one function that I often use a lot is how do I convert my numerical features, so label 1, into something that is like human readable. So what I can do is there's an int to string function, and if I put label 1 here, it should tell me indeed that corresponds to equivalent, which means that one sentence is a paraphrase of the other. And just as a sanity check, if we do 0, then it should be the same for not equivalent. And so this class label feature has some documentation on the hub with other functions you can look at. But I find this is quite a powerful way of quickly switching between labels that are numbers and labels that are strings, so that you can understand what's in your data set. So let's have a look. Are there any questions? Okay, so there's a question from IM Holmes. Is there a way to benefit from the convenience of the dataset library, but use a dataset that might be private, for example, customer data? Yes, that's a great question. And the answer is yes, you can. So previously, before I joined Hugging Face, I was working for a telecom company, and everything was like completely closed off in, on premise. We couldn't use Hugging Face Hub. So I actually had to solve this problem. So the way you could do this, or the way I used to do this most frequently, is I would actually use pandas. So I would say import pandas as PD. And then I would create my data frame. So let's suppose I'm going to just make a dummy data frame. So let's say I have, my data frame as follows, and I'm going to say, okay, let's call this, I don't know, text. Then I'm going to put hello world, and then maybe another element, g'day. Okay, and then I'll add another column, which is maybe the, let's say the label. And then maybe this is going to be positive. So this is a super simple data frame, but this is something that I would load locally. And of course, Pandas is amazing for data processing, but if you want to use the datasets functionality, what you can do is create your own dataset, your own custom dataset. So from datasets, you can import the dataset object itself. And then what we can do is we can create a dataset from let's see, so I think it's from, is it from Pandas, I think? And then this should, fingers crossed, create now a dataset object which has the features of text and label, has 2 rows. And if we now, for example, look at all the elements, we can see that indeed we've now got our own custom data set. So this is more or less how I used to work 90% of the time. I hope that answers your question, I'm Holmes. There are other ways of loading data. You can load it from CSV, you can load it from JSON. And I think that more or less covers most of the use cases. The only time things get a little bit painful is if you're dealing with very large data sets, things that maybe don't fit into a pandas data frame. But there's a streaming functionality that has just been implemented into the Datasets library. And so, yeah, I think basically you can cover almost all use cases this way. Okay, cool. So what we've just done so far is we've just loaded our raw data set. And the thing that we would like to do, right, is we'd like to tokenize this. So what we've been doing in all of the lessons so far is we've basically been tokenizing kind of like string by string, or like maybe a list of strings. So if we look at this example here, then when we do the tokenization, you can see that tokenizing the first sentence column is giving us now a list of input IDs. So we have now basically a set of input IDs. Well, let's just have a look at these guys. So yeah, we've got a big list of input IDs corresponding to the first sentence and also to the second sentence. And remember that these IDs is what we used to feed into the transformer. These are the things that go into the embedding layer and then into the transformer stack. And at the end, we get something like logits we can make predictions with. Okay, so that's the stuff we've been doing all the time. And you can also, as I think we may have seen, you can convert your IDs back to tokens using the convert IDs to tokens. But the thing that is like maybe most interesting or most common is how do you basically tokenize the whole data set? And the most common way to do this is to define a function. You can call it whatever you want. Here it's called Tokenized Function. And what this function will do is it will operate on every row of the data set and apply whatever you define the operation to be in that function. So once you've defined your function, you can then apply a map onto your data set. And then this will automatically tokenize every single row in your data set. So we've got all the raw strings, sentence 1, sentence 2, and it's converted them automatically into input IDs, and also this attention mask that we saw last week, where we needed to figure out how to sort of disable the padding tokens from the attention mechanism. So this is a very powerful way of kind of, in just more or less 1 or 2 lines of code, automatically tokenizing every single example in your data set. And it's very fast. It can be basically multi-processed, and it can also be run in a batched way on a GPU to be even faster. But maybe let's just like sort of look at a sort of very simple example just to break down what's going on here. So let's suppose I wanted to do something which is quite common, maybe adding a column. Now there are faster ways of doing this in datasets, but I'm going to show you how we could do this with a function. So let's add a column, and what this column should expect is an example, or let's just maybe even make it easier. It's a row. It's a row in our data set. And the main thing that this function needs to return is it has to return a dictionary. And the reason for that is if you look at one of our examples from the training set, you can see that it's kind of like a dictionary, right? We've got keys for the column name and value for the actual element, or the element in that, say, cell if it was a table. So what we need to do is we need to return, strange. It seems that Colab does too. Okay, so we need to return a dictionary, and I'm going to make something up. I'm going to say this is a new column, and I'm going to just make all the value of my new column be just a word, hello. Okay. And if we do this, then if I take my raw data sets, well, let's just take maybe the raw training data set, just to keep it simple. Then when we apply map, we just need to feed it this function, and it will then automatically create a new column and just add it to our raw data set. Now, one thing you should be aware of is that this operation is not in place. So if you're familiar with Pandas, there's often operations that are in place, which means you just run this line and then it kind of changes the state of the object. In datasets, most, if not all, operations are out of place. And so what this would mean is that if you wanted to actually have that column stored in your memory, you would create, dataset with, say, extra column or new column, and you would then do, that equals the map. And then when you look at this, you now see that we have a new column with hello. So that's been now sort of stored in the memory of this new dataset object. Okay, so just to recap, we need a function, and the function has to always return a dictionary where the key is the name of the column and the value is the value you want for that row. Cool, so let's take a small thing. Let's see, I am Holmes is asking, please could you explain what the attention mask does again? Okay, great, very good question. So let's have a look at this example here. So in this example, we've got two sentences, and we can see that this is maybe not a good example. Maybe let's add some padding. Okay, actually, what I need to do to show you an example is I'm going to, I'm going to do this. So I'm going to apply truncation in my function, and I'm going to add some padding. And then this is just to show you what we're talking about here. Okay, so here I've just tokenized the raw datasets, and I've got this tokenized datasets object. And let's get the first element, which hopefully will show us. Okay, this is a bit of a messy one. Okay, but let me just try to summarize. So remember in the last chapter, we looked at this concept of padding. And the reason we had to do padding is that all the operations that we do inside the transformer are basically matrix multiplication. And when you do matrix multiplication, you want to make sure that the matrices you're operating on are more or less square. So if I have, for example, one sentence and I represent this as a vector, then in order to compare one sentence to another sentence, it helps if those arrays or those vectors have the same size. And so padding is a technique where you can basically, in the simplest case, look at the longest sentence in your batch and then just put a 0 at the end of every other sentence, which basically pads out to the length of the longest one. And then this will guarantee that your sentence or your batch has all vectors of the same size. And then when you stack them together, you've now got something that's rectangular. Now, that's padding, and more or less we do it for just computational reasons. But the problem that it introduces is that the attention mechanism, you may remember from one of the earlier chapters, it basically takes an embedding, so these numerical representations that we have of the sequence, and it then updates them to create something called a contextualized embedding. And these contextualized embeddings essentially contain, for every token in that sequence, they contain information that relates the sort of meaning of that token relative to the whole sequence. So an example would be if I have a sentence like, I don't know, time flies like an arrow, then flies is a verb in that case. But if I have another sentence which is like fruit flies like a banana, then flies is an insect. And so the attention mechanism allows us to distinguish these two cases because the contextualized embedding that represents flies is different in those two cases, and it uses the whole sequence to develop that representation. Now, because attention operates on every single token in the sequence, it also operates on padding tokens. And this would be like a bit of a problem because these padding tokens are like these artificial things we injected just to make sure all the matrices are square. And so the attention mask is a way of saying to the attention mechanism, pay no attention to the padding tokens. And what an attention mask will look like here, it will have a bunch of ones. So these will be all the tokens at the start of the sequence that are just the things we want to develop contextualized embeddings for. And then at some point, you will hit the start of the padding sequence. So you've got all your words, and now you're just adding zeros to your token embeddings. And here, the attention mask will then switch to a 0, and that will, when it goes through the attention layer, it will just disable attention computations on that. So I hope that explains your question, Iron Holmes. It was a bit of a long-winded one. And so ones for all the input IDs. Correct, exactly right, yep. So all the input IDs which are not 0, or generally not 0, it will be a 1, and then it will be 0 for all the input IDs that are 0. So we can have a look here. All the input IDs are non-zero, and now we've got the padding IDs. Okay, great. So there's another question, which is from Resh Mashek. Can we do the reverse of a map function? Let me think if I understand what you mean. So what kind of example would you have in mind, Resh? Not sure I understand the question, but maybe you can write it in the chat and then I'll come back to it in a bit. Okay, so we've seen how to do tokenization across the whole data set using the map function. And the I think that's more or less the main thing in this collab. So I'm just going to delete this. And the other thing that is worth pointing out is there's kind of two ways you can do padding. So one way is to explicitly define the padding in the tokenization step. So what you do is you say padding true or however you wish to implement it. And then when you do tokenization with the map function, it will automatically pad all the sequences according to how you defined it. Now, the drawback with this is that when you do training, maybe your padding, for example, here, picked the longest sentence in the whole data set and then padded everything out to the thing in the whole data set. But when we do training, what we're really doing is we're doing training on batches. And so one thing that is quite common is to do something called dynamic padding, which we'll see shortly, which is a way of basically sort of adding the padding tokens on the fly. And this lets us do computations much more efficiently. So I think let's take a look at that video now. So let's have a look at how we can do padding on the fly.
What is dynamic padding? In the Batching Inputs Together video, we have seen that to be able to group inputs of different lengths in the same batch, we need to add padding tokens to all the short inputs until they are all of the same length. Here, for instance, the longest sentence is the third one, and we need to add 5, 2, or 7 pad tokens to the other sentences to have 4 sentences of the same length. When dealing with a whole dataset, there are various padding strategies we can apply. The most obvious one is to pad all the elements of the dataset to the same length. the length of the longest sample. This will then give us batches that all have the same shape, determined by the maximum sequence length. The downside is that batches composed from short sentences will have a lot of padding tokens, which will introduce more computations in the model we ultimately don't need. To avoid this, another strategy is to pad the elements when we batch them together, to the longest sentence inside the batch. This way, batches composed of short inputs will be smaller than the batch containing the longest sentence in the dataset. This will leave some nice speedup on CPU and GPU. The downside is that all batches will then have different shapes, which slows down things on accelerators like Tpus. Let's see how to apply both strategies in practice. We have actually seen how to apply fixed padding in the datasets overview video, when we preprocess the ArmorPC dataset. After loading the dataset on Tokenizer, we apply the tokenization to all the dataset with padding and truncation to make all samples of length 128. As a result, if we pass this dataset to a PyTorch data loader, we get batches of shape batch size, here 16, by 128. To apply dynamic padding, we must defer the padding to the batch preparation. So we remove that part from our tokenized function. We still leave the truncation part so that inputs that are bigger than the maximum length accepted by the model, usually 512, get truncated to that length. Then we pad our samples dynamically by using a data collater. Those classes in the Transformers library are responsible for applying all the final preprocessing needed before forming a batch. Here, data collater with padding will pad the samples to the maximum length inside the batch of sentences. We pass it to the PyTorch data loader as a collate function, then observe that the batches generated have various lengths, all way below the 128 from before. Dynamic batching will almost always be faster on CPUs and GPUs, so you should apply it if you can. Remember to switch back to fixed padding, however, if you run your training script on TPUs or need batches of fixed shapes.
Okay, so that was a nice explanation of dynamic padding. So just to summarize, if I have a data set with say 1,000 examples, and let's suppose that one example is just way longer than all the others, maybe there's an error or something. So if I just did my tokenization on this data set, as we just did before in the Colab, and we just pad to the maximum length of the longest example, then all the samples will get pushed out to this very long one. And so we'll have a lot of zeros everywhere that we have to then do computations on, which are slower. So the alternative is that since we do most of our training in terms of batches, that we just pad at the batch level. So instead of padding for the whole data set, we just look at the elements in a batch and we pad to the longest, for example, element in that batch or the longest example in that batch. And what this will do is it will then require less computation, so it'll be faster. But the downside, as Sylvain explained, is that each batch will have different sizes. So we're going to have, maybe in one batch, the sentence is only 10 tokens long for the longest one. So everything is 10 tokens long. Maybe the second batch is 30 and so on. So in the Transformers library, we have what are called data collaters. And these data collaters are basically functions that allow us to kind of cleverly package together all these different size batches in a way that we can then do training efficiently. So let's maybe look at some questions and then just revisit this data collator stuff. So there's a question from, let's see. Okay, so we've got a question from Unz, which says, hi, there's a limited label datasets that aren't English. Would it make sense to machine translate a dataset to a certain language or domain specific genre to fine tune on? Yes, that's a very good question and generally highly recommended. So a good example of this is there's a dataset called MLQA. And this is a multilingual question answering dataset. And the authors of this dataset basically translated the squad dataset, which is in English, into several languages. So I think they have German, Spanish, Hindi, Vietnamese, simplified Chinese. So this is one way of creating data in your domain or your language, which you can then build models on. The only drawback is that it's often been known that if you're training like very large transformer models, they can learn somehow that there's a translation that's been made, and they'll take shortcuts to get good performance. So in the end, the model that you get on your translated text, it may be good just in the translated context, but if you then deploy this with real human interactions, then this could be sort of out of domain, and maybe the model has only really learned how to detect that it was translated and not how to actually solve the task you care about. So you have to be a bit careful with this, but it's something that is worth trying, and it's something I've used as well. In Switzerland, where I live, there are 4 national languages plus English. And so most of the time you don't have data in English, it comes in Italian or French. And so you need to do some of this translation tricks. And one thing that came out recently, which is I think quite cool, is Facebook released a model called M2M 100. And this model is a translation model. So it's a sequence, or it's an encoder-decoder transformer that we saw in chapter 1. And it can do basically translations across 100 different languages. So you imagine you've got basically 100 by 100 matrix of all the languages. And for every single pair, you can do a translation. And so this gives you 9,900 pairs you can translate across. And it's a very good model. So if you're looking to do translation, I would recommend using this if your language is in the 100 that they cover. Okay, and then maybe to revisit Resha's question, how could you revert the column that was created before in the map? Okay, now I understand what you're asking. So the question is, let's suppose we've added this column, and we've now got a data set with a new column, which says hello. I'll show you the specific one for this example is like, if I want to delete the column, then what I can do is I can remove columns. And then here, I just need to provide a list of column names. So I could provide new column, and then this will delete the new column and recover back the original data set that we had. That more or less, I think, would cover most of the cases that you want to undo the map operation. The only time it won't really work is if you then do other things to your data set. Maybe you change the content of these original columns, and then undoing that isn't easily done. Okay, and now we have another question by SRM Suma, which is, why is dynamic padding slow on TPUs compared to GPUs? Is there any intuition behind this? Okay, so this is testing my very limited TPU knowledge, but my understanding, very limited understanding, is that it's a sort of fundamentally different architecture for basically doing numerical algebra, linear algebra, or algebraic equations, or multiplications of matrices. And I think it's simply just due to the way that the chips are designed that they are much more efficient if everything is a fixed sized matrix, and you're not trying to do this like shuffling of data to do the collation. But Omar, who's in the chat as Hacker Llama, he used to work at Google, so he can maybe provide a much better answer in the chat. So yeah, this is it's a very good question. I would also really like to know a detailed answer, so that'd be cool to know. Okay, so what I wanted to do before we start training the model is just have a quick look at this, what this data collation is doing. So in transformers, there are different data collaters to basically handle this dynamic padding. And the one that most of the time we use is data collator with padding. And what this will do is, let's see, can I see it? Yeah. If I get a few samples from my data set, what I've got here in my samples is just a list of, the tokenized inputs, and they've got the same length for their input IDs. So they've been, that's probably because I added padding. So let me get rid of padding here. Sorry. So I'm just going to re-tokenize my data without the padding in the tokenizer because we want to do dynamic padding. And one thing that's very cool, I didn't really mention, is that in datasets, all the operations that you do are cached. So they're basically stored as arrow tables in your hard drive. And so then when you want to reprocess, it basically checks, have I done this computation before? And if it does, it will just load the cached version. And that's extremely fast. So you can see that, it took like a second. And this is very cool if you've done something that, you process like 1 million examples and then you restart the notebook and you don't want to have to wait again to reprocess them. The cache will just do that instantaneously. Okay, good. So now I've got, I've tokenized my data. I have no padding. So all the examples are of different lengths. And so what the data collator will do when I pass it through these samples is it will automatically resize in that batch all the samples to the longest length in that batch. So you can see here that the longest example has 67 tokens. And so what it's done now is it's created tensors, each of which have essentially 67 columns, for each of the longest tokens, and some of those will have padding. And that's what the data collator has done for us. And then when we do training, it will do all of that for us on the fly. Yeah, exactly. So the question that SRM Suma is asking about the TPUs is that square matrices are what GPUs like as well. Yes, that's true. So if I'm not mistaken, the TPU context is to do with this distinction of whether you do dynamic padding or not. And with dynamic padding, we are kind of creating square matrices on a batch level, but we're also moving data around. So we're having to sort of kind of dynamically create data on the fly with different shapes. And my suspicion is that's the thing that maybe slows it down. But it's a great question, and I should look up the answer at some point. Cool. So it's you've asked a very good question that stumped the two guys in the course. So great, thanks. Okay, cool. So that's more or less datasets tokenization. Let's now take a look at training. So what we're going to do is look at the trainer API. So I'll launch the video.
The trainer API. The Transformers library provides a trainer API that allows you to easily fine-tune Transformers models on your dataset. The trainer class takes your datasets, your model, as well as the training hyperparameters, and can perform the training on any kind of setup. CPU, GPU, multiple GPUs, Tpus. It can also compute the predictions on any dataset, and if you provided metrics, evaluate your model on any dataset. It can also handle final data processing, such as dynamic padding, as long as you provide the tokenizer or a given data collator. We'll try this API in the MRPC dataset, since it's relatively small and easy to preprocess. As we saw in the datasets overview video, or though we can preprocess it. We do not apply padding during the preprocessing, as we will use dynamic padding with our data collator with padding. Note that we don't do the final steps of renaming, removing columns, or set the format to torch tensors. The trainer will do all of this automatically for us by analyzing the model signature. The last step before creating the trainer are to define our model and some training hyperparameters. We saw how to do the first in the model API video. For the second, we use the training argument class. It only takes a path to a folder where results and checkpoint will be saved. But you can also customize all the hyperparameters the trainer will use: learning rate, number of training epochs, etc. It's then very easy to create a trainer and launch a training. This should display a progress bar, And after a few minutes, if you're running on a GPU, you should have the training finished. The result will be rather anticlimactic, however, as you will only get a training loss, which doesn't really tell you anything about how well your model is performing. This is because we didn't specify any metric for the evaluation. To get those metrics, we'll first gather the predictions on the whole evaluation set using the predict method. It returns a named tuple with 3 fields: prediction, which contains the model predictions, label IDs, which contains the labels if your dataset had them, and metrics, which is empty here. We're trying to do that. The predictions are the logits of the models for all the sentences in the dataset, so an array of shape 408 by 2. To match them with our labels, we need to take the maximum logit for each prediction to know which of the 2 classes was predicted. We do this with the argmax function. Then we can use the metrics from the Datasets library. It can be loaded as easily as a dataset with the load metric function, and it returns the evaluation metric used for the dataset. We can see our model did learn something, as it is 85.7% accurate. To monitor the evaluation metrics during training, we need to define a compute metric function that does the same step as before. It takes a named tuple with predictions and labels, and must return a dictionary with the metrics we want to keep track of. By passing the epoch evaluation strategy to our training arguments, we tell the trainer to evaluate at the end of every epoch. Launching a training inside a notebook will then display a progress bar and complete the table you see here as you pass every epoch.
Okay, so that was a lot of information. If you've never seen the trainer, it might have been too many things at once. So what we're going to do is kind of walk through this together. And then hopefully at the end of this, you'll then have all the tools you need to start training your own models and solving your own problems. So in Google Colab, there are different runtimes available. So by default, most of the time it's like a CPU, so there's no acceleration. And so what you need to do is hit runtime, select the runtime type, and for this notebook, we're going to use a GPU. Later, we'll see how to use a TPU. So then we save this, and now this is going to launch in Google Colab sort of a machine that has a GPU in the back end. And one thing you can do to check what kind of GPU you're running is to do Nvidia Smi. And let's see what we get if it wakes up. So here we've got a Tesla Katie. So these are most of the time the sort of default GPU you get. They're not super great. But if you look online, you can often find there's people who have saved the state of things like P100 collabs, and then you can just use them, and then they're very fast. And of course, if you reset the runtime, so this is sometimes a hack if I'm trying to get a better GPU, you can do factory reset, and then this will just wipe the whole backend, and hopefully should now still be a GPU. Yep. And maybe we'll get something a little bit different to a K. Let's see what we get. Okay, I'm still stuck with a Katie, but sometimes if you're lucky, it will give you a P100 or even a Tesla. Okay, so we've got our GPU-backed Colab now. So again, we do the same thing. We install our dependencies, and what we have here in this code is just the same things we did before. So we load a data set, and then we define a tokenizer from a checkpoint. So we're using BERT base uncased. We have our tokenized function. And what this tokenized function is doing is it's taking the two sentences. Remember that this data set is about trying to predict whether one sentence is a paraphrase of another. So we pass both sentences to the tokenizer. We use truncation is true, so that if one of the sentences is longer than the maximum sequence length of BERT, which is 512 tokens, it will just truncate it to 512. And then we tokenize everything, and we define this data collator so we can do dynamic padding. So I'm just going to run that. and it should be pretty fast. Okay, so while that's running, let's start by looking at this training arguments. This is the first thing that you encounter with the trainer. So training arguments, you can think of it as just like a config. It's basically a class where you can define various hyperparameters for training. And the only thing you need to specify is an output directory where all the information from the training will be stored. Or if you save the model, this is where it will go. So if we look at training arguments, we can see that, let's see, can we see through here? You can see that we have this output directory, and then there's a huge range of things, like really a lot. You can specify the learning rate, you can specify the parameters of the optimizer, you can define the optimizer, you can define callbacks, kind of like FastAI, which is no surprise because Sylvain developed the trainer. And these callbacks allow you to control training in clever ways, like early stopping and things like this. So I won't go through all of this, but there's basically a large number of parameters you can set, and you can find that in the documentation for the trainer. And it comes with some pretty good defaults. So most of the time, it will just work out of the box. So now we need to load a model, and we're specifying two labels because we've got just two classes. Is it a paraphrase or not? And again, it's a sequence classification model because we're doing text classification. And then comes the next bit, which is maybe the more complicated part. So we need to instantiate a trainer. So a trainer, more or less at minimum, needs a few things. It needs a model. So this is the model that we're going to train. It needs training arguments. These are the things that define how the training will operate. And it needs one of a few data sets. So it needs either a training data set or evaluation data set or a test set. And you can have one and none of the others, but it needs at least one thing. It basically needs at least one data set generally that you want to train on. You can instantiate it without it, but generally you want to specify one. So here we're passing the tokenized data, and that's important. You don't want to pass the raw data to your trainer because it will feed it to the model, and then the model will go, I don't know what you're doing, or what I should do with these strings. And the other two things that are kind of interesting is passing a data collator and a tokenizer. So providing these two arguments will do dynamic padding, which will be faster for training. And the way it works is you say, hey, give me a collator, and there are different types of data collator, but the one we're using is the most common one. And it also needs a tokenizer. So it's basically the way the data collator works is it kind of combines the tokenizer with the batching to work out how to arrange the inputs. And so by providing these two arguments, we will then get some speed up in training. And so this will instantiate the trainer. And let's see if it works. Fingers crossed. Okay, good. So one thing that I usually do before I launch training is I just do like a sanity check that I can run the evaluate function, because a lot of the time what happens is when you run trainer.train, you will train for some number of steps, and then you will evaluate, maybe at the end of an epoch, and that's kind of like one of the default strategies. But then, if your evaluation, maybe your metrics are not implemented correctly or whatever, if your evaluation fails, then you're going to fail after waiting for a whole training of one epoch, and that's like really annoying. So a sort of sanity check that I do is just to make sure that I can run evaluate. And if that works, then I'm relatively confident that the training run will work. And what you can see that this evaluation has done is it's given us some information about the number of examples in the validation set, and it's provided us with a value of the loss, and then some kind of runtime metrics, so sort of how performant is this at processing batches. And so obviously this is a random model at the moment. We've just initialized BERT as a backbone and just stacked on like a linear layer with random weights. So this is kind of a garbage loss. So the goal will be, after training, for this to be going down. Cool. So I'm going to now run the training, and this takes a few minutes. So while it's running, we'll then watch the accelerate video, which will show us how to, well, maybe not. Maybe I'll just run this and then see if there's any questions. Okay. So DK Crazy Div asks, we're using BERT base uncased, and the article mentions word piece for BERT, but we pip installed transformer sentence piece. Are we using it here? If I were to reverse engineer, how would I programmatically get from checkpoint and figure out which tokenizer? That's a great question. So the question we have is, why are we doing pip install transformers sentence piece? So this is an optional dependency, which is a different tokenization algorithm that is used by models like XLM Revert. And it's listed as an optional dependency because it's a bit heavy. So if you don't want to use any models that don't require sentence piece for the tokenization, you can just leave it and it will work. So for example, if we just did pip install with transformers, we will get word piece for free. It will come part of it. But if we want to use these other models, we have to define explicitly the sentence piece dependency. So that's like maybe clarifies the first part of the question. We're always using word piece with BERT, and we only install sentence piece for the models when we need it. And the reason we have it in the course is because there are some cases later in the future parts where we're going to be using the sentence piece tokenizer. And so it's just useful if we just always have access to it. Okay, so if I were to reverse engineer, how would I programmatically get from checkpoint to figuring out which tokenizer to use? Okay, so maybe we can, I'll answer this in two ways. So the simplest way is the following. In transformers, we have an auto model class for different types of models. So this auto model will just do the encoding, and we also have auto tokenizer. And import. And these classes, they do this pairing. So if I take auto tokenizer from pre-trained and I put BERT base uncased, it will automatically assign the tokenizer that was associated with that checkpoint and then load it into my tokenization or my tokenizer object. And similarly, if I do auto model from pre-trained and I do the same checkpoint, it will automatically figure out that for that checkpoint, I need these set of weights. So the most important thing that you need to know is just to make sure that you use the same checkpoint for both the tokenizer and the model when you do the from pre-trained. And so what I often do in my code is I'll have an explicit variable, which is BERT base uncased, like this, and then I'll just load this variable into all of my pre-trained calls, so that then I know that they're matched. Okay, so that's sort of, let's say, standard way of how we link these things together. Now, you're asking how could we programmatically get from checkpoint to tokenizer? So let's have a look at what's inside one of these model files. Let's just check that my training is working. Yep, good. Okay, so in the model, we have a config, and this config, let's see. Okay, so the config tells us the name of the checkpoint. So if you wanted to programmatically make sure that, I mean, let's suppose you start with like the config. I guess what you could do is you could then use this attribute as the thing that you feed to the tokenizer. So for example, I could do tokenizer equals auto tokenizer from pre-trained, and then I would take my model, I would take my config, and then I would access, what is it? Is it name or path? Can I access this as an attribute? Yeah, so I could do this. So I could load my tokenizer this way, and then this would, let's say, guarantee that the checkpoints match. But to be honest, this is like a bit complicated. So I would more often than not just recommend defining a variable with your checkpoint and then just feeding that variable into your tokenizer model. So I hope that answers that question, DK Crazy Div. But feel free to ask if it's not clear. Okay, so our model is pretty close to being done with the training, and you can see that by default in the trainer, every 500 steps, the model will run an evaluation on the validation set and log the loss by default. So this is just the training loss. But the thing that Sylvain explained in the video is that what we really want to do is compute metrics like accuracy or F1 score or whatever. And so the way you do this in practice is you define a function called compute metrics. And this metrics function has to basically return a dictionary where you have a key corresponding to the name of the metric and then the values that you would compute from your predictions. And so in this example here, Sylvain is leveraging the Datasets Library, which has its own metrics as well. And then once you have loaded the metric for this task in Glue, you just have to extract the predictions and the ground truth labels. And then you can just do metric.compute, and this will automatically create this dictionary for you, which you can then feed into the trainer as follows. So you can do compute metrics like this. And then what this will do is that every 500 steps by default, it will then compute the metrics in addition to the training loss. And this is quite handy because this is how you can track the performance of the model on the validation set as you train, and you can make decisions about, okay, is it getting better or not? Okay, so let's just have a look at this. So, okay, so good. The model is trained. And you can see that the training loss here is around 0.35. We saw when we did the evaluation loss, it was roughly double, and that was with the random weights. So now if I run evaluate again, I should see, hopefully the loss has gone down. Huh, okay, it's gone up. That's very interesting. I'm not sure why that's the case. So I'm going to just say that's the demo gods being mean to me. Generally, this should have gone down. Unusual. Might just be a random fluctuation in what we've done. Okay, and so just to sort of dig down a little bit into how we build this metrics function, the trainer has a predict method, and you can just feed into that predict method a data set from datasets. And this predicts method will return an object called predictions. And let's have a look. So this predictions is a prediction output object. It's just like a data class which has attributes, and the attributes it has are predictions. So if we look at predictions, oops, that's not going to work. It's just an array of basically all of the logits from the model. And we also have the ground truth labels listed like as IDs. So this is, paraphrase, not paraphrase, not paraphrase, so on and so forth. So the main work you often have to do when you build your compute metrics function is you need to convert your logits into, let's say, integers or label IDs, because that's the thing that you want to compare against. And so one way to do that is to just compute an argmax, which will basically say for every prediction in terms of logits, find the index with the largest or the highest logit. And so then once we apply that, our preds now is a tensor of integers. And then I can feed those predictions into my, my metric from datasets, and then I can run compute on that, and it should hopefully give us these values. So any questions about computing metrics? Okay. So I'm not going to run this last cell. It's just the same thing we did before. It will run the training, but instead of showing the training loss, it will show the validation metrics that we use. But I encourage you to play with this yourself, maybe with a new data set, just to understand how this is really working. Okay, so that's the trainer API. This is what I use, let's say, 90% of the time. It's just very convenient. It works, and it means I don't have to think too much about writing my own low-level training script or my training code, which can often be error-prone, right? And so a good reason to use like high-level APIs like the trainer or Fast AI or PyTorch Lightning or whatever is that they abstract away a lot of the boilerplate code, which if you do it yourself will probably have mistakes. And this has been kind of battle tested through thousands of users. Okay, so to wrap up the session, I want to now look at something that's like really exciting, for me at least, is Sylvain developed a library called Accelerate, which says, sometimes I really need to have control of the training loop. And you can do this on CPU and GPU pretty easily. There's lots of tutorials on doing that. But there's been a kind of, say, trend in the last few years towards having access to like multi GPU or TPU machines. And these offer, in principle, a lot of speed up because you can now distribute your training. So, you can distribute your batches to these devices, do your computations on these devices, and then do back propagation through the whole, say, cluster of devices. But in practice, it's been very difficult to do this as a beginner. And that's because you have to understand all this distributed setup in PyTorch or TensorFlow. And again, many ways to make errors, and keeping track of how data is basically parallelized across nodes is a bit of a pain. So this Accelerate library is designed to make this simple for us. And so let's take a look at the final video. Is it this one? Here we go.
Supercharge your PyTorch training loop with Hugging Face Accelerate. There are multiple setups on which you can run your training. It could be on CPU, GPUs, TPUs, distributed on one machine with several devices, or even several machines, often called nodes, with multiple devices. On top of that, there are new tweaks to make your training faster or more efficient, like mixed precision and deep speed. Each of those setups, or training tweak, requires you to change the code of your training loop in one way or another, and to learn a new API. All those setups are handled by the trainer API, and there are also several third-party libraries that can help. The problem with those is that they can feel like a black box, and that it might not be easy to implement the tweak to the training loop you need. Accelerate has been designed specifically to let you retain full control over your training loop and be as non-intrusive as possible. With just 4 lines of code to add to your training loop, here shown as the example of the training loop video, Accelerate will handle all the setups and training tweaks mentioned on the first slide. It's only one API to learn and master instead of 10 different ones. More specifically, you have to import and instantiate an accelerator object that will handle all the necessary code for your specific setup. Then, you have to send it the model, optimizer, and data loaders you're using in the prepare method. This is the main method to remember. Accelerate handles device placement, so you don't need to put your batch on the specific device you're using. Finally, you have to replace the loss.backward line by accelerate tor.backward loss. And that's all you need. Accelerate also handles distributed evaluation. You can still use a classic evaluation loop, such as the one we saw in the training loop video, in which case all processes will perform the full evaluation. To use a distributed evaluation, you just have to adapt your evaluation loop like this. Pass along the evaluation data loader to the accelerator.prepare method, like for training. Then you can dismiss the line that places the batch on the proper device, and just before passing your predictions and labels to your metric, use accelerator.gather to gather together the predictions and labels from each process. A distributed training script has to be launched several times on different processes, for instance, one per GPU you're using. You can use the PyTorch tools to do that if you're familiar with them. But Accelerate also provides an easy API to configure your setup and launch your training script. In a terminal, run accelerate config and answer the small questionnaire to generate a configuration file with all the relevant information. Then, you can just run accelerate launch, followed by the path to your training script. In a notebook, you can use the notebook launcher function to launch your training.
Okay, so before we have a look at low-level training loops in PyTorch and Accelerate, there's a question from Ebstan who says, can I find out how many labeled samples do we need to get good results with transfer learning and fine-tuning? Is there a rule of thumb here? That's a really, really good question. At least in my experience, the answer really depends on the task that you're trying to tackle. So generally speaking, and you know, the language that you're dealing with and the domain. So these are all factors to consider. A rough hierarchy, at least from my perspective, is that text classification is generally one of the simpler tasks to tackle with this. And in a sort of standard text classification context, you may only need maybe 100 samples with transfer learning to get quite good results. And of course, the thing that you should always do is build a baseline. So build a really, really simple model, not a transformer. Do something like naive Bayes or logistic regression or something like this, just as a sanity check that on your small data set, your results, when they transfer from the training set to the validation set, because there's a really, really good chance of overfitting here. So roughly a few, like 100 to a few hundred samples for text classification, at least for me, has worked well. But then it gets a bit harder as you do different tasks. So if you move to, say, question answering, here there's like, say, two strategies you can take. So one strategy, which is maybe the first one to start with, is if you're doing question answering or extractive question answering like Squad, is to look for a model that has been trained already on Squad in your domain, ideally. So let's suppose I was doing Squad in German, which is a bit different to the standard case. Maybe I look for Squad here, and let's see. I believe there's a German Squad, and maybe I can specify the language to German. Okay, we don't have that. So let's have a look. I believe there's a company called Deepset who have done this. It's called Quad. Okay, so here is a German, here is basically a language model that has been fine-tuned on a German version of Squad. And now this lets you answer questions in German. Then I would take this model, and if my corpus is in German, but it's like, custom, maybe it's my business data, I would then just try to see how this model works on that data set. Now, generally, you'll find that it doesn't perform as good as the original squad model. And then you would do some, say, domain adaptation from the squad model to your domain. So you basically just do a little bit of fine tuning on your domain, and typically you'll then see the model adapts to your corpus, and you'll get much better performance. And in that context, for say question answering, typically you need like on the scale of a few thousand, 1,000 to a few thousand examples to get at least good results. But you have to be very careful because sometimes when you do this domain adaptation from one model to another, if you sort of overfit your domain, you will end up forgetting all of the good features that the fine-tuned model had to start with. And so it's generally tricky in that sense. And then for other tasks, like named entity recognition, this is I think very problem specific. It really depends on the entities, what are the like frequencies of the entities that you have, and here again, I think you're dealing with on the scale of like a few thousand examples to get okay results. So to summarize, okay, well, just to summarize, I'll answer the question. So to summarize, we're talking about maybe a few hundred examples, labeled examples for simple problems like text classification, to a few thousand for the labeled case, and maybe even more if you're doing something that's very niche. I mean, if you're doing, maybe I'm doing like maybe like legal analysis of legal contracts, and maybe the domain is so different from any existing pre-trained model that I actually need to do some sort of fine tuning on a legal corpus that looks like what I have. And so then you don't need labeled data per se, you just need a lot of unlabeled legal contracts that you can then fine tune a language model and then transfer to your domain. Okay, so there's a follow-up question which says, thank you for the answer. What if I have more than a few hundred of classes for a task? Okay, yes, so then that then gets very hard. I would put that in, so maybe for text classification, there's like a hierarchy of complexity. So the simplest case is like binary classification, and then maybe multi-class is after that, and then maybe multi-class with like, extreme number of labels, like 100 or 1,000 different labels or different categories, and then maybe multi-label is like somewhere around that. So I think in general it will be harder, and what you will find if you have a data set which has like 100 classes or more is that the model will be very confident about the majority class. So there's always a distribution generally in these classes, and most of the time it's like a power law. So you'll have a few classes that are very common, and then there'll be some that are quite rare just because they're tags or something that people don't really use very often. So the model will struggle a lot in those rare tasks, in those rare tags or those rare labels. And so then what I would recommend you do is you try to focus on the hard examples. So you try to collect more data for those rare examples to boost the signal for the model. So you don't need maybe like 100 more examples of the common class, you need 100 more examples of the rare ones. But in general, as long as you can kind of get like a good coverage in the labels, it should work, except it's just going to be tough because, with 100 options, the model has more chances to make mistakes. And in fact, there's a very good trick I should mention, is that when you train a model, you can extract or compute the loss that the model has on every single sample. And if you do this, this will tell you roughly which examples the model is most confused about. And this is actually a technique from FastAI. Well, I don't know if they invented it, but at least this is where I first saw it. And let's see if we look here at FastAI. So I think it's called most confused. Let's see. Okay, so things have changed a bit in V2. Okay, I can't quite find it, but basically in the FastAI library, they have a function which lets you plot the most confused examples that the model is having trouble with. And then with those, you can then work out where you need to collect more data. But roughly speaking, what's happening is it just computes the loss for every example in your validation set and then just sorts them. And so if you do that yourself manually, you'll be able to see where you need to improve the model. Okay, so let's wrap up by diving into the Accelerate library. So the difference here is that instead of using the GPU, we're going to use the TPU hardware in the back end. So we activate it this way, and we install transformers and data sets as we always have. And the main thing that you need to do now is you need to install some Accelerate and some TPU specific libraries. So in order to run PyTorch on a TPU, we need some special wheels, they're called, or basically a binary file that we can install here. And this will then allow us to run PyTorch on TPU. And the first thing we do is always the same. It's like we just tokenize the data. So this is pretty familiar by now. And one thing that Sylvain is doing here is he's removing all of the text columns or the columns that we don't really want for training explicitly. This is to make it easier so that the trainer doesn't get confused when it receives raw text. And he's also renaming the label column to labels, and this just helps the trainer auto-detect which column it should compute the metrics on. And the other thing that he's doing is setting the format of the elements in the dataset to PyTorch tensors. So I'm just going to show you that just quickly. So if we look at our tokenized datasets train, oops. We look at one element. Now, what we've seen so far in today's session is that everything was just a Python list. But you can change the format of your data set from lists to tensors, but you can also set them to TensorFlow tensors if you're running TensorFlow, or even I think you can do it for NumPy arrays. So it really depends on what you're operating on that you want to manipulate, but this is a very handy way of switching the formats. Oops. So yeah, Torch or PyTorch does it. Okay, because we're not using the trainer and we're going to use our own training loop, we need to have what are called data loaders. So in PyTorch, there's kind of two concepts that are important. One is like the concept of a data set. So these are the things that we've been doing most of the time so far. But then when you want to feed batches to your model, there's an API called Data Loader, which will automatically sample from the data set and then provide those samples to the model. So you basically feed in the data set you care about, and then you can feed in whether you want to randomly shuffle the elements, and that's important for training, just in case you have some ordering in your data that is artificial. You can specify the batch size and also how the collation is done for the dynamic padding, so to speak. Okay, so you can create a data loader, and then if you look at an element of a data loader, it's just going to be basically a set of tensors associated with each batch. And then we instantiate our model just like we always have. And then once this is loaded, we can just do a sanity check that if we feed a single batch, which just has input IDs, attention to mask label, and these other IDs I won't talk about, it returns a tensor, which is the loss. So this is like a sanity check that our model is working. And because we're going low level into the training loop, now we also have to specify the optimization algorithm for basically minimizing the loss function. So I would say the default, a very good default, is to use this modified atom called atom W. And you can just use the default learning rate, and you just pass the parameters of your model that you want to optimize. So just to show you quickly, if we have a look at this, this is a generator, so I need to create a list. And then if I just look at one of these elements, you can see that the parameters of the model consists of tensors. So these are like our weights and biases, along with a name that tells us, which layer we're looking at. And so by feeding these to Atom, we're basically saying, here is my instructions of weights and biases I want you to optimize, and then it will proceed when we do the training to do the optimization. And there's also some extra things we need to specify, like the number of epochs, the number of training steps, and the scheduler for how we want to sort of control the learning rate during training. So if these concepts are kind of the first time you've seen them, we have information in the course notes to help you understand that. But basically speaking, using a constant learning rate throughout training is suboptimal, both in terms of speed and in terms of just getting to like a good local minimum. And so we have schedulers which will essentially control how the learning rate increases and decreases during training. And so we can define the scheduler. Did I not define the optimizer? Okay, so I'm just going to load this. This is just an example when you're doing things on a GPU, you specify the device. And this is then more or less what a training loop looks like in PyTorch. So you say, we're going to do training now. So we're going to activate dropout in the model. And then we loop over for every epoch. And every single epoch, we're going to loop over every single batch in the training data loader. And then we're going to set those tensors to the device we care about. We're going to compute the loss. And then we're going to just do the backward pass in PyTorch. And then we just basically take a step now with the optimizer and the scheduler, and then we update. And this will then just do training in a normal way on a GPU or a CPU. But the thing that's kind of cool is that we're using a TPU. So in a TPU, we have 8 cores on Colab. And so what we want to do is we want to basically be able to do distributed training this way. And there's a nice kind of picture here of what's going on with distributed training, where I'll put this in the chat. You can have a bunch of different machines, and each machine has its own process. So you can think of each process as being like its own little, like, say, controller that is processing data. And so what we can do with a TPU is we can think of it as having 8 different processes, and we need to communicate the sharing of weights, essentially how we do backpropagation across these processes. And the Accelerate library allows us to do that very simply by basically we define something called an accelerator, and then we have to prepare the data loader, the evaluation data loader, and the model using this accelerator API. And this will automatically work out what hardware I'm running, how many cores I have, how should I distribute the data, how I should, basically copy the model across these nodes or these devices. And then everything else after that is exactly the same as we saw before. So you don't really have to change anything in your training script. It's basically untouched. It's just the way you prepare the training loop. So if you run this, it won't work as it stands. What we need to do is we need to wrap all of the accelerator code inside a training function. And so if we do that, we just need to put all of this inside a training function. And one thing I discovered yesterday is we need to make sure that the data loaders we use here are, let's have a quick look. are not global variables. Let's have a look. I think I just do this. Okay, so here I'm just initializing a model. I'm initializing the optimizer as we did before. And here the magic of Accelerate is basically going to do all this distributed placement for us. And so it's going to give us a data loaders, a model, and an optimizer. And then everything else runs as normal. And this is where this question about tokenizing the data is important. So what we've been doing previously is using dynamic padding. So we don't use padding in the tokenizer directly. And in fact, here, if you look at when I tokenized the data, where is it? Here, in my tokenizing function, I just use truncation. But because we're running on a TPU, I want to activate padding. So I need to put padding equals true. And I'm going to specify the max length that I want to pad, not to the max length of the full model because it's too large. I'm just going to specify kind of arbitrarily that it's 128 tokens. And so once you've padded all your inputs, we can then wrap our, we need to then also re-instantiate the data loaders here. And now we can create a training function, and fingers crossed, this will then allow us to launch a TPU training. So okay, so while that's working, let's have a quick look at the questions. Okay, so there's a question from I'm Holmes. There is a Hugging Face Twitch session today and tomorrow, all labels chapter 3. The main difference is the time zones. So we try to capture people who live on the sort of east and west of globe. And there's also a TensorFlow session tonight with Matt Carrigan. And so that's for all the TensorFlow aficionados. There's a question from Uns about regarding the domain-specific cases for text classification. Before I train my model for my downstream task, would it make sense to pre-fine-tune with language modeling to better understand the context? Yes, in general, that's a very good thing to do. It will the amount of boost you'll get in performance is very dependent on the domain shift. So if I have BERT, which was pre-trained on Wikipedia, and my text is kind of like, say, factual or kind of like Wikipedia, then the boost I get from fine-tuning BERT on my corpus won't be so much. But if my corpus is like very different in domain, like maybe it's like source code or something like this, then you will see typically a bigger boost in performance. So it's always worth doing, and in general, it's pretty easy to do. There's a question about if I want to classify articles instead of sentences, does BERT and friends still work, or should I look at something like long format? That's a great question. So BERT is basically limited, or most of these sort of vanilla models are limited to 512 tokens. So if your documents are longer than that, you'll have to do one or two things. Use a model which can process longer sequences like long forma or big bird. From memory, I think they can process 4,096 tokens, so they're much, much bigger, like 8 times bigger than BERT. But if that's not like sufficient, you'll then have to basically chunk or kind of split your document into passages, and then you'll have to feed those passages into the model and then do some aggregation to work out how you build up a kind of representation for the full document that you can then feed into your classification head. There's a question about to improve the baseline model, take a Revert model, train it. Yes, that's right. Exactly. I Am Holmes asks, what is the difference between using PyTorch's default Atom W and the Transformers one? That's a good question. Off the top of my head, I don't know. My guess is that there are some, I mean, there's a long history of Atom and not being implemented correctly. So yeah, off the top of my head, I have a suspicion that perhaps the Transformers one is correct, and the PyTorch one maybe isn't. But maybe do some experiments, find out. Sorry, I don't know that off the top of my head. Okay, cool. So those are more or less the questions. Let's see, something went wrong, and this is now where I get to do some debugging. So let's have a look. I got an error, and it says you should probably activate truncation or padding with padding equals true to have batched tensors with the same length. Okay, so I clearly did something wrong when I defined my data loader. So let's have a look at what went wrong. So I first tokenized my data, which is good. I then need to set the format. I want to get rid of this collate function. This collate function is going to be the thing that gave us problems. Okay, so now I should be able to launch the TPU training. Okay, so this is now launching on these 8 TPU cores, and fingers crossed, I didn't make any mistakes. Great, thanks for the feedback. I am Holmes and DK Crazy Div. I'm hoping you're enjoying it, and thanks for the questions. So this looks like it's training, and yes, great. Oh no, we have a problem. Okay, so what is it? Stack expects tensor to be equal size, but got 96. Okay, so okay, so here I'm going to do some, I know we're running over time, so I apologize. I'm going to see, let's see if I can debug this fast, and if not, then I'll just fix the notebook later. Okay, so basically I'm running into an error, and this is a good way of seeing how TPUs are a little bit more fun than normal. It's saying the stack expects each tensor to be equal size, but got 96 at entry 0 and 100 at entry 1. So this is suggesting to me that somehow I've screwed up the tokenization. So instead of having everything with the same shape, there's some like something's gone wrong. So let's have a look at my data loader. Okay, so let's have a look at my tokenization first. So when I did tokenization, I set padding equals true and max length. And so now when I look at my tokenized data sets, let's have a look at, so maybe let's have a look at the input IDs. So the input IDs, we want these to all be the same shape. And I'm going to just take, let's just take, say, 10 of them. And then what I'm going to do is I'm just going to say tensor.size for tensor in this. So let's see what we get. Okay, so this is telling me that all the tensors have the same size, which is good. Let's just do a sanity check if I go from the end. Yep, looks good. Okay, so my tensors are all the same size. And should just do this again. And let's see, now what is complaining on about this invalid type? Because I need to return tensors equals PyTorch. This is so annoying. Okay, let's not do that. Let's do padding. And Then let's remove the column. Let's set the format. Good. Okay, now let's see what we get here. Okay, so we can see there's already a problem. Interesting. So, Cool. All right, so we're going to try and debug this. And in fact, if someone sees what I'm doing wrong, this will be great. So here's a problem. The problem is I've created a data loader here, train data loader, and it's complaining that when I try to put the tensors together, they're somehow not of the same shape. So let's see, what have I done wrong? Okay, so let's do that. So let's look at the first batch, and let's look at okay, let's look at the input IDs, and then let's look at the size of each tensor in here. So it seems that my tokenized data sets are not the ones I was looking for. So let's have a look what's going on. If I look at so we saw before that these were meant to be 89 in size. So let's have a look at this, and then we go t.size for t in here. Okay, so you can see that in my tokenized data sets, all the inputs have size 89, but for some reason in the batch of the training loader, everything is 71. So let's see. Why would that be different? Why would the batch be different? Don't tell me I need this collate function. No, that's not what I want, because now they're going to be dynamically padded. That's an interesting thing. I'm going to have a look. So let's see if we have. So just to tell you what I've done. So I've reintroduced a collate function into the data loader here. I was pretty sure we don't want to have that because we want to have fixed sizes. But let's see if this has sort of magically debugged the problem. Okay, so for reasons I don't understand, adding a collate function to the data loader seems to have been important for letting us do the training. And you can see here I'm doing on one TPU core, I'm running the training, and what should all these messages, right? You can see here, these are the warning messages you often get when you instantiate a model. And so what Accelerate has done is it's copied the model into the 8 TPU cores, but done so in a way that the initialization is the same. So we've got the same model at the start, and then it should instantiate another 7 parallel trainings. So now we're training the model copied in 8 pieces across 8 cores, and each core will get its own batch of data And then backpropagation will be synchronized so that then when we update the model, we update based on the losses computed for every device. So this is, yeah, obviously a little bit of a hack. I'm a bit unhappy that it's everything I said about needing to use padding seems to have been mixed up with the collate function. But yeah, that's the joy of live coding. Maybe you can dive into this yourself and try to understand exactly, you know, how one needs to set this up. There's something I'm still kind of missing in my head at the moment. But nevertheless, that's let's say training on a TPU. And one thing that I would recommend you do as like a homework problem is try to work through these training notebooks on a new data set. And so you can find many options on the hub. So if you go to datasets, you can look at text classification. And for most of the time, this will cover all the things. You have everything you need now to study this. And the other thing that you can do is, for example, we're doing paraphrase detection, right? We're checking if two sentences are paraphrases of another. Another example of this would be the Quora dataset. And this is a very common problem on things like Stack Overflow or Quora, where you've got people asking questions, and sometimes the questions are duplicate, and you often rely on the community to flag a question as duplicate or not. And so this would be a nice data set to use, which would be very similar to what we've done, but give you a kind of different flavor of dealing with different columns and different inputs. So I'm going to put that in the chat as a suggestion. And yeah, I would also recommend see if you can get the TPU training working. I think TPUs are a very exciting development because they offer, in principle, 8 times as much speed up in principle, but reality is around 3 times over conventional, say, GPU training. And they're free on Colab. So now you can use Accelerate to train faster than normal and do really cool distributed stuff. All right, so that was a bit longer, and sorry for that. That's my fault for not being able to debug my own code. So I hope you enjoyed it. And tonight there's Matt doing TensorFlow, if you're into that. And I think tomorrow is then Sylvan doing the next round of this. And next week we're going to be diving into the sort of more advanced parts of the library. So what we're going to be doing next week is how do we share models in the hub? How do we push everything to the hub? How do we share metrics? And so this is going to be the kind of icing on the cake for everything we're doing. So I'm not back for chapter 4, but Omar is, and Omar is awesome. He's in the chat right now, and so you should definitely come. I'll actually be in the chat, so it'll be like a body swap. And so I hope you guys see you then. Cool. So with that, I'm going to stop recording and stop the stream. So if you have any questions, just put them in the forum, and see you next time.